Welcome back to section 6.3, Vectors in a Plane. This video will cover examples 4 through 7 in your notes. So you should be able to write vectors as linear combinations of a unit vector. You should be able to find the direction angle of a vector and use vectors to model and solve real-life problems. Let's go ahead and get started. So in many applications of vectors, it's useful to find a unit vector that has the same direction as a given vector v. So let's take a look at what this means. So say you've got this vector v, and it's got a magnitude that's not equal to 1. So more often than not, it's much easier to find this other vector u that has a magnitude of 1. So sometimes we have to stretch v or compress v in order to make the magnitude of vector u 1. So in order to find this unit vector, we take the vector that's given and just simply divide by the magnitude of this vector. So let's look at an example together. We're given that vector v in component form is -2, 5. So let's get that sketched in here first. So starting at the origin, -2, +5. Our goal is to get a unit vector that has magnitude 1, that has the same direction, also starting at the origin. So it's going to be shorter. So we need to compress vector v. So in order to do that, we first need to find what is the magnitude of vector v. Well, because it's in component form, I can simply square each of the x and the y. So working on the inside, it looks like 4 + 25. So the magnitude of vector v is the square root of 29. Now to find vector u, we simply take vector v and divide by the magnitude of vector v. So let's do that together. So vector v is -2/5. Divide by the magnitude, square root of 29. So now our x and our y component both need to get divided by. So vector u comes out to be -2/√29, comma 5/√29. Stylistically, you should rationalize both of these. I'm going to let you do that yourself. Now we simply need to verify that vector u does indeed have a magnitude of 1. So because vector u is in component form, I can simply take the square root of the square of the sum of 2/√29 and 5/√29. So let's do that. So the square root of -2/√29, square that, square of 5/√29 squared. Let's clean these up. So if I square this, square the numerator, square the denominator, I get 4/, square root of 29 squared is just 29. Let's clean up the second piece as well. So square the numerator, square the denominator, get 25/29. Remember, there are implied parentheses around this sum, so we need to add them and then take the square roots. So because I have a common denominator of 29, I can simply add across the top. 4 + 25 is 29, which reduces to the square root of 1, which is indeed 1. All right, go ahead and try exercise 49 in your notes now. Make sure you get a quick sketch of this. Remember, if you were to draw a triangle starting at the origin with length of -1 and +1, the magnitude is not equal to 1, applying the Pythagorean theorem. Check your answer in the back of the book. Come back when you're done. The unit vector 1, 0 and 0, 1 are called the standard unit vectors and are denoted by lowercase I and lowercase j. And it's worth noting here that we use either a boldface or I with the arrowhead over to distinguish it from the imaginary number I being square root of -1. So say you've got this vector v, whatever that is, we can actually separate it into its vertical and horizontal components. So let's say we've got vector v as being 3, 4. So its horizontal components can be rewritten as 3 times how far horizontal are we going, plus how far vertically are we going. So I just swapped out I and j, so I can rewrite vector v as being 3i plus 4j. So when it's written in terms of I and j, this is called a linear combination of the vector. And again, they're assumed to be in standard position. So let's take a look at an example here together. So let u be the vector with initial point 2, -5, and terminal point -1, 3. So we need to write it as a linear combination of the standard unit vectors I and j. Well, that's not so bad. We've got from 2, -5, all the way to -1, 3. So let's go ahead and get this into component form first. So vector u, so we always subtract terminal x minus initial x, comma, terminal y minus initial y. So plugging in values, terminal x is -1, initial x is 2, comma, terminal y is 3, initial y is -5, so plus 5. So in component form, we've got vector u as being -3, 8. Now to write this as a linear combination, we simply replace I and j. So it looks like vector u is -3i plus 8j. Nothing more than that to it. All right, go ahead and try exercise 63 in your notes. I would get it in component form first, and then write it as a linear combination of vectors I and j. Check your answer in the back of the book. Come back when you're done. In example 6, we're given that vector u and vector v, and asked to find the difference of 2u minus 3v. Now the problem is given to us as a linear combination, so I see no reason to convert it into component form. So let's just plug in values. So 2 times vector u is -3i plus 8j minus 3v, so 2i minus j. Let's clean this up. So we've got -6i plus 16j minus 6i plus 3j. Combine like terms, so we've got -12i plus 19j. Now remember, as a linear combination, we're not expressing it as vectors, so we don't need vector notation. Now it is worth noting that we could have done this by converting vector u and vector v into standard form. So we could have said, well, 2 times vector u, so -3 and 8, so I'm using component form, minus 3 times vector v, 2, comma, -1. Let's clean this up. So the first vector is -6, 16. I want to distribute this negative. So by distributing the negative, the sign between the two vectors becomes positive. -6, comma, +3. Now adding -6 to -6, we get -12, and 16 plus 3 is 19. So same answer two ways, either as a linear combination or as a vector in component form. Your choice. All right, go ahead and try exercise 69 in your notes now. They're telling you that u is 2i minus j, and vector w is I plus 2j. So I see that they're giving us vectors u and w in as linear combinations, so I see no reason to change it. Check your answer in the back of the book. Come back when you're done. So say you've got vector u, and vector u is a unit vector, such that theta is the angle measured from the positive x-axis to u. So if vector u is a unit vector, we know the magnitude of this vector has to be 1. So let's go ahead and get vector u drawn in here. Now what's great about the magnitude being 1 is we know that this terminal point must lie on the unit circle. And what's great about that is we can pull in all of our knowledge about the relationships of the unit circle in order to simplify further calculations. So here's theta, and here's the point x comma y that lies in the unit circle. So drawing a quick triangle in here, or angle, here's x, here's y. But we know that sine of theta is equal to adjacent over hypotenuse. So my y value, if I cross multiply, is equal to sine of theta times 1, or y is just simply sine of theta. Similar argument, we know that cosine of this angle theta is adjacent over hypotenuse. So if we cross multiply, x is simply cosine of theta times 1, or cosine of theta. So this point x comma y can be swapped out with cosine of theta for x, sine of theta for y. So with that in mind, we can rewrite vector u as cosine of theta, sine of theta. Now, what's not explicit in this vector is it's got a magnitude of 1. It's drawn in there, but it's often left out. So, of course, this is in component form. As a linear combination, abbreviated LC, we can say vector u is equal to cosine of theta I plus sine of theta j. And again, what's not explicit is it's 1 times cosine of theta I, the magnitude, plus 1 times sine of theta j. At this point, it's helpful to remember that a linear combination is always expressed as a I plus b j. So vector u, your a value is 1 times cosine of theta, and your b value is 1 sine of theta. And that's going to come in handy here when we start looking for the direction of unknown vectors. Now suppose we don't have a unit vector. Suppose instead we've got some other vector called v that's in the same direction as u, but it's either shorter or longer. And just for ease of demonstration here, let's assume that it's longer. So we can rewrite as in component form vector v as being the magnitude of vector v times cosine of theta sine of theta. And then we would multiply the magnitude in. As a linear combination though, vector v is equal to the magnitude of vector v times cosine of theta I plus the magnitude of vector v sine of theta j. So again, knowing that vector v is in the form a I plus b j, your a value is magnitude of vector v times cosine, and your b value is magnitude of vector v times sine of theta. So remember, theta is the angle that vector v makes with the positive x-axis. We can continue drawing this triangle in here. So my horizontal component would be magnitude of vector v cosine of theta, and the vertical component of this triangle would be magnitude of vector v times sine of theta. All right, from our quotient identities, we know that the tangent of theta is equal to my vertical component over my horizontal. From this triangle, I see my vertical component is magnitude of vector v times sine of theta, all over my horizontal, so magnitude of vector v times cosine of theta. But remember, a linear combination is always expressed for vector v as ai plus bj. And earlier, we said that our a value was magnitude of vector v cosine, and our b value was magnitude of vector v times sine of theta. So with this substitution, we're going to swap this out with a and swap out the denominator with b. I can say that tangent of theta is equal to b over a. So in order to actually find the direction vector, we would use the inverse tangent of b over a, and that'll give us theta. So quick reminder, the inverse tangent of x is defined on the domain negative pi over 2 to positive pi over 2, or unit circle-wise from negative pi over 2 to positive pi over 2. So we've got 0 here, we've got pi over 6, pi over 4, pi over 3, pi over 2, negative pi over 6, negative pi over 4, negative pi over 3. So with this in mind, we need to be really careful that when we use our calculator, we use it with discretion. If I take the inverse tan of some b over a, and I get a negative 32 degrees, I'm always going to find a positive coterminal angle. So I would need to add 360 degrees and come up with 328 degrees. So we're always trying to find theta between 0 and 360 degrees. Another common situation that occurs when we use our calculator is we've got a vector whose resultant is actually in quadrant 3. But when we plug it inverse tangent of some b over a, and we get negative 32 degrees again, but we know in this case that our resultant vector is in quadrant 3, we actually have to add 180 degrees to this result and come up with 148 degrees. Similarly, if we have a resultant vector that is in the 4th quadrant, and we take the inverse tan of b over a and come up with, I don't know, for example, 40 degrees, but we're in the 4th quadrant, we would again need to add 180 degrees and come up with 220 degrees. So make sure you're always trying to find a value of theta between 0 and 360. In this first scenario, we added 360 degrees because we were in quadrant 4 and wanted to be, but we needed to find a coterminal angle. In situation number 2 and number 3, it gave us an answer that was in the wrong quadrant, so we needed to add 180 degrees. All right, so let's go ahead and try some examples together. All right, so let's find the direction angle of the following vectors. In A, we've got vector u as being 3i plus 3j. So your a value is 3, your b value is j. So we've got tangent of theta equals b over a. So we've got 3 over 3. Take the inverse. Well, 3 over 3 is 1 equals theta. So plugging this into our calculator. All right, so let's plug this into our calculator, but before we do so, let's make sure we're in degree mode. So second tan of 1 equals 45 degrees, which makes sense because we're in quadrant 1. So theta is 45 degrees. For b, we've got vector v is 3i minus 4j. So over 3 down 4. So tangent of theta is your b over your a. Take the inverse, come out with theta, grab your calculator, second tan, negative 4 over 3. Let's see, it came out to negative 53.1 degrees. But remember, we're always looking for theta between 0 and 360 degrees. So I need to find a coterminal angle by adding 360 degrees. So my theta is approximately 306.9 degrees. All right, go ahead and try exercise 77. So negative 2i minus 5j looks like you're going to be working in quadrant 3. Remember that inverse tan of theta is defined only on the interval from negative pi over 2 to pi over 2. So my hunch is that when you take the inverse tangent, you will need to add 180 degrees to get a result in quadrant 3. Check your answer in the back of the book. Come back when you're done. All right, and go ahead and try the wrap up for examples 4 through 7 in your notes now. Number 1, you're just finding a unit vector. So take a look at example 4. Do make sure that you verify using the distance formula that it's got a magnitude of 1. Number 2, write it as a linear combination. So you're using i's and j's. Number 3, make sure you distribute in order to find 2u minus 3v. Number 4, you should not need a calculator for A. For B, you probably will need to use a calculator. Make sure you express those answers between 0 and 360 degrees. And on example 5, on problem number 5, they're giving you that angle, that theta is equal to 30 degrees, and magnitude is equal to 6. So in component form, what is vector v? And as a linear combination, what is vector v? All right, come to class tomorrow with questions. I'll see you soon.